Let's look at one way to implement a singly linked list, or in other words, a linked list where each node only points to the next data in the list. So to do that, I've got some test code set up here, and the very first thing that we will need is a node class. Now, I'm going to write the node class as an inner class to the linked list class itself. This will allow the node to access data from the linked list and the linked list to access data from the node without any getter or setter methods. Our users really should not have to know that nodes exist in the first place, and they should never really have to interact with those nodes or change things about them. Sometimes when you write a linked list class for a project, you will write some getters or setters or things like that that will return nodes. And that's mostly so that the test cases can check out the inner workings of your linked list and make sure that it's all valid. But for when we're creating code that others might use, we really shouldn't give them access to the inner workings and the guts of our program, nor should they need to have that. They should be able to put things into a linked list, like adding at the head or adding at the tail, and they should be able to get things out without any real hassle. So my nodes need data. I'm going to write this linked list to work with integers. You may write ones that work with other type of data. And then here, I'm going to set up the next variable so that from a node, we can get the next thing. And because I'm only writing them as an inner class, I don't need a bunch of setters and getters for them. What I do need is I need some abilities to add things to the list at the head, at the tail. I'll focus on the things that a linked list is good for and not the things that you could add on, like adding in the middle, which it doesn't perform quite so well at, as we've seen in class. And then we'll get from the head, get from the tail, and there's a sort of implied call to the toString in my tests down here that means we'll want to write a toString, or otherwise all we'll get is memory addresses from that. So we'll create first the add head and add tail methods. They'll be void because they change things. They're mutators. They will need to take the data that's going to be inserted into the list. We'll need an add tail that fits the same basic structure. And we will need some getters for the head and the tail, which will return the data, not the node. Yours for projects may return the node again so that we can actually examine those nodes, but here we're just going to return the data so that users could get the data back. Return, which reminds me, we will need placeholders, we will need variables to store the head and the tail as nodes. Head. We don't know what those are up front, so we'll just create the variables for them. We can't set values for them until we've been asked to add data as the head or the tail. Now I can get the head or I can get the tail. They will be null at first, but that's okay. We'll write functions that add to them as well. Then last, public string toString, so that I can print out the whole list nicely. You may remember that I like to set up variables of the type I'm going to return and then write a statement to return them rather than returning nulls or things like that that might mess up some of my tests before I've finished. And then in the middle, my only job is to build the string from the list's data. So the hard work here will be adding at the head and adding at the tail. Once we've got that set up, then we're going to be able to build things on the list. So adding the head, we need to stop and think about the fact that sometimes there will be nothing in my list. For example, when the head is null. That means there was no data in my list to start with, which means that I need to add something and make it the head, also make it the tail, because if the head was null, there is no tail either. The first task that I might do here is to create a new node variable, a local one, and create a new node from the data, because nodes, again, just hold on to data for us and then point us to where the next data will be. Well, my nodes don't have a constructor, so I can just create a new node and set the data if I wanted to as well. Great. And so now the head will be n and the tail will be n. And now I have a list that has exactly one node, one item in it. I should probably also return here because I'm done. If the head was null, there was nothing in the list. This was an empty list. And so therefore, I'm just making a node and setting it as both the head and the tail. If the head was not null, then I have to think about taking that new node that I've created and linking it in so that it is the head and that my old head is now the second item in the list. So what I might want to do is to just say head equals n. However, if I do that first, I've lost track of where the old head was, and I no longer have a variable that points to it. So the first thing that I have to do is to set n's next to point to the current head, and then set the head to be n. And then I should be all done with the job that I need to do here. Adding at the tail will look pretty similar. In fact, we can steal most of that starting code there because if the head was null, the tail was null. It might feel a little more comfortable to say if the tail is null here because it's in our add tail, but hopefully we've maintained a list where if the head was null, the tail should also be null because that is an empty list. And then I again might be tempted to try to set the tail equal to n because I'm adding at the tail, but I would lose track of my old tail. So the first thing that I should do is take the current tail and set its next to point to n so that the current tail will, if we're stepping forward through the list, will now point us to n, and n will be marked as the tail in my list. So this should work for the first few tests that I have here. Let's run it and find out. Okay, I've added 7 at the head, then I made 12 the head, so 7 should become the second item in the list. Then I added 5 at the head, so 12 should be second and 7 should be third. Then I added 10 at the tail, so when I ask for the head, I get back 5, the last thing added at the head. And when I ask for the tail, I get back 10, the last thing that was added at the tail. My print line does nothing now, so let's work on that. Building the string from the list will require that basic structure that we've set up probably a few times at this point if you've worked through other linked list uses, not necessarily writing a linked list, where we take some current variable and we start it at the head. And then we say, while that current variable is not null, we'll keep looping. And inside that loop, the step part of our loop will be to set current equal to current.next. This will allow us to start at the head, go to the next item, the next item, the next item, and once we've reached the tail, then the next from the tail should be null. Many people try to write their loop condition to stop when they've reached the tail. Often that ends up leading you to skip the data that's at the tail of your list. So here what I'm going to want to do is to add in the items from the list one by one so that we can print out the whole list. So for example, we will take our return string and we will add to it current data plus a space so that we can tell where the different data is separated. We will have an extra space at the end of our string on this, and if that matters to you, you might need to trim it off here at the end, or you might do something to stop a second early and add the last item or things like that. I'm going to leave it on just for the sake of simplicity in our testing here. Now when I run again, I should get 5, 10, and the whole list. We see 5 is the head because it was the head added last, 12 is second, 7 is third, and 10 got added as the tail. That gives us a functioning linked list that we can add things to and get them back, but what we cannot do is remove things from the linked list. So I want us now to look at writing some functions to remove things from this singly linked list. It will be void. Sometimes you'll return the data that you got from the node that you're removing. We won't worry about that here. We're going to have a function for removing the head. We're going to have a function for removing the tail. And that will be enough for us here. Again, if you want to write a fully featured linked list that has things that linked lists aren't even particularly good at, then you could have ones to remove based on an index or things like that too. So removing the head will be easy if our list is empty, if our head is null. So let's first worry about if the head is not equal to null, so that if we try to remove from a linked list that's empty, we just do nothing. So as long as the head is not equal to null, then what I'm going to need to do is to set the head equal to head.next. Now, in a singly linked list, this is all I should need to do, because this will move my head forward to the next item. Nothing will point to my original head, and therefore Java will notice that eventually and will garbage collect it for us. It will delete it from memory and free up that space for us. That's really not too difficult in a singly linked list to remove the head. In a singly linked list, however, removing the tail can be much more complicated. Oh, I forgot one particular case, and that is if the head is equal to the tail, then we've got a list that will be becoming empty, and we need to remove, actually can do this inside of there. We need to remove both the head and the tail. So if the head is equal to the tail, that means there's only one item, and we should result in an empty list. This looks a little funny because the tail will be set to null, and then the head will implicitly be set to null. Some people would like to write this as a separate sort of, actually, we can now remove our head not equal to null here, because head would be equal to tail in this case, and we can set head equal to null. And now we've got a beautiful setup where, I don't want that commented, where the tail is set to null, the head is set to null, and we could return there. And that will stop us from ever doing the head equals head next here. That cleans up a little bit. So if the head equals the tail, either because they are both null, or because there's only one item left, we can set the tail to null and the head to null, and we can return because we're done. We've emptied the list now. Whether it was empty or not already doesn't really matter. If the list is not empty, then we just set head equal to head next. So this will give me a little bit of code to work with, copying down to here for removing the tail. Removing the tail in a singly linked list is actually much more complicated because we don't have a place to step back to. With the head, we step forward by one, and that removes the head. With the tail, we have no way to quickly step back to the node that we would create as the new tail, or that we would change to be the new tail. So to solve that, we're going to need our basic loop structure here to start at the head and to step forward until we are at the node just before the tail. While current next is not equal to tail, meaning we will stop when we see a node that is just before the tail. That will be the one that will become our new tail. So our loop will only start us at the head and step us forward until we're at the node that's just before the tail. Then what I need to do is set tail equal to current. Before I can do that, I should set current's next to null so that I no longer step forward to the tail I'm trying to remove. Let's save that. Let's try out our tests for removing. So I've got a test that will remove, or I've got a step that will remove the head and a step that will remove the tail. I get the head and get the tail, and then I print out the whole list again. Let's see if it works. It did. We can see that from that list 5, 12, 7, 10, we removed the head, which was 5, and we removed the tail, which was 10. We are left with just the 12 and the 7 from the middle. If you're writing your own code and you want to test it very thoroughly, I'd recommend also removing all the way down to an empty list and make sure that it successfully can remove that last item too, because you saw we needed a special case for it. So our basic singly linked list can be very simple in a lot of the cases of things that we want to do for it. Getting the head and the tail are very simple. Even the toString is just that basic loop we've gotten used to. And the adding at the head and the tail is not too hard. If it's empty list, then we need a special case for that. Removing from the head is also very simple. Removing from the tail, however, is complicated and takes more time. All of the other methods are constant time, O of 1, and the removing the tail is linear time, O of n. We'll see in a moment how we can improve on that when we look at doubly linked lists.